want to start this video by talking a little bit about something that you saw in the other video, but talking specifically about closed pipes versus open pipes and why it works the way that it does, and really make the connection with the sound waves and longitudinal waves, that type of thing. Also to talk about, there's two different scenarios with pipes that we often end up with. One is where we have an open pipe or a closed pipe and wind is passing over it, causing some type of resonance or something at a fundamental frequency, which gives us a pitch. The second scenario is where we have something that creates a pitch and we have to have a specific tube that then allows it to have resonance. But you know, it's a different situation, each one of those. So I want to make sure to talk about it. Okay, so the first thing is closed versus open. Okay, now you learned about the first harmonic in the last video, the one that you watched with me. And the idea here is when we have a closed pipe, anytime there's a closed pipe, there has to be a node on the closed end. Okay, the molecules there aren't vibrating. Remember, when we draw this wave, even though it is going from the top to the middle down to the bottom, the wave isn't actually moving up and down like this, right? We're talking about a pipe. We're talking about sound in the pipe, and sound is a longitudinal wave. So even though we're drawing it up and down, the particles aren't actually moving up and down. They start at equilibrium, and when the wave is up at the top, it actually means that particle is moving over to the right. And when the wave is down at the bottom, that actually means it's moving over to the left. So this standing wave here that's sometimes up and then sometimes down is showing that this particle is moving to the right, to the left, to the right, to the left. It's vibrating back and forth because it's a sound wave, and that's how sound works, is the particle is moving back and forth from the right to the left. Now, of course, the particle here on the wall can't move because it's on the wall. That's why here it has to be a node. Okay? Even if this isn't a nice antinode, on the wall, we're going to get a node. Okay, that's just how it works. Okay, so when we have that, only if we have the antinode here, I don't know why it keeps doing that on me, only here are we going to get an antinode, and that's where we get the most resonance possible. Okay, on an open pipe, you have to have that on both ends. Okay, there's no way to have a node over here, and so therefore the particle is going, if you want resonance, if you want that sound from the pipe, the particle needs to have its maximum motion on both sides of the pipe. Okay, so this is why a closed pipe has to be the way that it is, and an open pipe has to be the way it is, because of how the particles can move in those boundaries. Sometimes we call these the boundary conditions. When it's open and when it's closed, what is that boundary like? Well, in this situation, it can't move. And in this situation, if we want resonance, if we want the loudest sound possible, it's got to be moving a lot. Okay? Now, with that, you know, you get the other harmonics. That's what it talked about in the other video. I'm not going to go into that too much. But I do want to look at this question right here. What is the difference between the sound produced by a tuning fork and the sound produced by a wind blowing past an organ pipe? Because these are two different situations, both of which come up in IB exams quite often. Okay, so first look at a tuning fork, right? So a tuning fork has a very specific frequency. So if I've got a pipe here, let's just take a closed pipe, and I strike a tuning fork, the tuning fork vibrates with a very specific frequency. Now, a specific frequency means a specific wavelength. Okay? Now, in order for me to get resonance in a closed pipe, it has to be open, it has to have an antinode here, and it's got to have a node on the far wall. But in order for that, but what if the frequency of the tuning fork is not right for that? What if the frequency of a tuning fork gives me something like this, right? So if that's the length of the wave, well, if I have a node here, then that means that my wave's going to look something like this, and I'm not actually going to get an antinode at the open end, right? So what needs to happen? Well, if I can change my pipe, right? If I can fill my pipe with water or make it go lower in the water or something, if I can fill it up to this point, right? The wave which now went like this is going to have a node there at the surface of the water, and now it's going to bounce back up, and now I'm going to have the antinode. All right? So for a tuning fork, the pipe has to be changed so that it has a very specific length to match the frequency that's already being created by a tuning fork. Not any pipe will give you resonance unless you change its length so that it's appropriate. All right? Now, that's quite different for a open or closed pipe, right? An open or closed pipe, if I have a pipe that is like this, and I start blowing air across it, right, with a, say this is an organ or a pitch pipe, like Peter Pan's pipe that he plays, something like that. All of those, whether it be open or closed, not an important point. But in this situation, I blow the air across, and it automatically creates this fundamental frequency, right? Whole bunch of things are happening here, but the fundamental is the one that's going to resonate, and it's going to allow me to get a certain pitch. Okay. Another place that you see this is like bottles, glass bottles, right? You put some water in them and you blow across the top and you get a pitch. This is why, because when you blow across the top, it is going to give you the pitch that matches the length of the pipe. The pipe or the bottle has this very specific length, and the pitch that you hear is the fundamental frequency that's being created there. Okay. What happens when you put water in it? Well, the frequency doesn't stay the same, right? The pitch created now is going to be the pitch which specifically will give you that first harmonic, right? Which means now that my wave has to be shorter, right? Because now I've got a wave, a quarter of a wavelength right there, instead of going the full length of the pipe. And so therefore a shorter wavelength, if the wavelength goes down, if the velocity is staying the same, velocity equals frequency times wavelength, the wavelength goes down, the frequency is going to have to go up, and I'm going to get a higher pitch. Okay? That's why when you have pipes, right, open pipes, right, like this, like Peter Pan's lute or whatever, right, and these are all open pipes, a little bit longer there, okay? When you have open pipes, the short pipe, in order to get the first harmonic, the one that's going to be most strongest, is going to go open node to open node, right? So very short wave there. The next one is going to go open node to open node, right? And you can already see that that wavelength is significantly larger, right? A larger wavelength means what about the frequency? Well, wavelength goes up, the longer wave here, because I'm still looking at the first harmonic, no matter how big the pipe is, longer wavelength means lower frequency, lower pitch. And so every time I go to a longer pipe, it's always going to give me this setup, because that's what happens when I blow the air across the top. It's going to automatically give me the first harmonic that fits the pipe that's there. And so that's the big difference between sound produced by a tuning fork and sound produced by wind blowing through a pipe. When you blow the wind, the wavelength is going to be fixed based off of the size of the pipe, and the frequency will correspond to that. In the tuning fork, you have to have a specific frequency. So therefore, only if the pipe matches the correct length, okay, only in that situation will you actually get the resonance. Okay, so two different situations there that hopefully you'll be able to deal with as you go on to new types of questions. All right, so that's it. Let's go on to the next slide. So we're going to continue with this video and talk about a little bit more with the standing waves and really develop some of those ideas, some of the conceptual things, some of the terminology that maybe you're going to see a little bit later on, and hopefully address some of the types of questions that you may see. And so that's what we hope to do in the next few minutes as we finish up this video. All right, so here's the first question that we're looking at. The first harmonic frequency for a particular organ pipe is 330 hertz. The pipe is closed at one end and open at the other. what is the frequency of the second harmonic, and why do we not care? Okay, very good. So first of all, the first question is pretty easy. What is the frequency of the second harmonic? Well, in order to get the second harmonic, you just need to double the first harmonic, right? You double the first harmonic, that's the answer. So the answer to what is the frequency? Well, the frequency is 660 hertz. Okay, that's easy enough. 660 hertz will be the frequency of our second harmonic. Now, the question, why do we not care? That requires us to have a little bit of understanding of what's going on here. So in order to do that, I'm going to go ahead and draw a picture, right? So first, I'm going to draw the original situation, which is our first harmonic. Okay, now remember, for a closed pipe, I need to have a node down here at this side. The reason why I have to have the node is so that it's not, because it can't be vibrating if it's on that wall. Okay, and then I need an antinode right here, which means I need to have as much vibrations as absolutely possible, because that's what's going to give the resonance and allow me to hear the sound. Okay, now at one point in time, the wave should look something like this, right? And then it's going to go through every single other position, but then it's going to go down to this right here. Okay, now remember that the wave doesn't look like this right now. This is what it looks like over time. It moves back and forth. This is a standing wave, just like when you pluck the string, right? When you pluck the string, the wave isn't always up there and it's not always down there. When I draw a picture on a string, it's not always like this and like that, right? It starts here and then it moves down to there and then it moves back up to the top, right? So that's what it looks like on a string. The same thing is happening here in the pipe, is that the wave starts in one position, this one up here at the top, and then it goes down to the bottom position and then back up. Now, again, in a pipe, this is actually not a transverse wave, it's a longitudinal wave, which means the particles aren't actually going up and down. That's how we draw the wave, but the particles aren't moving up and down. The particles are actually moving side to side. So this right here actually represents the fact that the particle is moving from the right to the left in that open mouth of the pipe. And that's the basic understanding of what's happening. Now, how does this play into why do we not care? Okay, well, if I have double the frequency, right, and there's a couple of ways you could go about this. You could, because we know that velocity equals wavelength times frequency, you could put in the speed of sound, right, in the air, though it doesn't give it here. You should know that it's about 300, maybe 330 meters per second, and you could work with that, and that would be fine, okay? And then you'd be able to calculate a wavelength, and then you could change the frequency, keep the same speed, and find out what the wavelength is there, and find out how that affects the pipe. Okay, now you can also do this very conceptually, right? If my frequency doubles, because I've gone to the second harmonic now, so if the frequency doubles, what's going to happen in order for the speed of sound to stay the same? What has to happen to the wavelength? Well, the wavelength is going to have to be 1/2, half of what it was before. Okay? Now, in this situation up here, the first situation that I had, in order to go from the top to the center and then down to the bottom, how long is this pipe, right? How much of a wavelength do I actually have inside of that pipe at any given point in time? Well, think about this. It goes from the top to the middle, down to the bottom, back to the middle, and then up to the top again. That's a complete wave. And if I break that into 4 pieces, top to middle, middle to bottom, bottom to middle, middle to top, that then gives me 4 pieces, right? Which means I only have one of those 4 pieces, and even my first grader who's now learning about fractions would then be able to tell you that that's 1/4. That's a quarter of a wave that is within the pipe. Okay? Now, if a quarter of the wave is within the pipe there, what would it look like if the wavelength became half of what it was before? Well, now instead of only fitting a quarter of wave in here, if my wavelength is shorter, right? Well, let's see. So my wavelength is half of what it used to be. It's shorter. So instead of only being able to fit in a quarter of my wave, if my wave is half as long, I should be able to fit in twice as much of it, right? Which means if I had an open antinode here, right? If there was an antinode, what would it look like? Well, I should be able to fit in, instead of a quarter of a wave, I can fit in half a wave now, right? Because the wave's shorter. So it would have to look like this. But that's a problem with a closed pipe because the molecules here can't vibrate back and forth because that vibration would carry it through the closed end where it can't go. It has to be an antinode there. So that can't happen. I can't hear the sound. Okay, what's really happening here is the question. Well, given that there has to be an antinode on the other side because that particle cannot vibrate, given that this can't vibrate, what would happen if I had half a wavelength? Well, from the middle of a wave, half a wave would take you through a crest or through a trough right back to the middle again. So it would look like either this or that. That's what my standing wave would look like if I had one that was created. Okay? Now, what do you see here? Do you see a particle that's vibrating back and forth, creating sound? No. You see a node. And because there's a node there, it actually won't create any sound. So why do we not care that the frequency of the second harmonic is 660? Because we can't hear it. We can't hear it because that specific situation for a closed pipe gives us that situation where we have a node at the end. All right? Okay? Let's move on to the last part of the question. Okay? If we now open the closed end, what will be the first harmonic frequency of the open pipe? Okay? Well, what does it look like if I open it? Okay, now I'm going to draw this one down here at the bottom. Okay, so it's the same pipe as before. I'm going to do my best to give more or less the same length there. Okay, so this one down here and that one up there have the same length. In order to get the first harmonic frequency, what does it have to look like? Okay, remember that means that I'm going to need an antinode here because I need the vibration at the end because there's nothing holding that in place, so I need an antinode there. And I also need an antinode at the other open end. Okay, so this is going back to what we learned last class. Okay, so if I draw that, the simplest way, the most fundamental way for that to happen is something like this. Again, remember both of these don't exist at the same time. This is a representation of that molecule moving back and forth. Okay? Now, in order for that to happen, how long is this wave? Well, it's going from a maximum down to a minimum, or from a minimum up to a maximum. That right there is half of a wave. Okay, so the pipe here needs to be half of the wavelength. Okay, and we did just talk about the fact that if the wavelength is half as big, the frequency must be double. So therefore, the first harmonic frequency of an open pipe must be 660 hertz. And in the case of the open pipe, we care because we can hear it. All right? Questions? I guess I can't ask them right now. If you have questions, ask me on Teams. I'll help you out. Okay? We're going to move this along because I got another couple of questions I want us to look at conceptually. Okay? In a standing wave, do adjacent antinodes have the same frequency? Do they have the same amplitude? And do they have the same phase? Okay, so we're looking at a standing wave now. And I'll actually talk about both a traveling wave and a standing wave here, right? So in a standing wave, right, this particle is fixed. I'll draw one that has maybe a couple of nodes, right? So it doesn't really matter, but this is where it originally was. Okay, so it looks something like this. Okay, and then it goes down to there. Okay, so there's my standing wave. Okay, my traveling wave, remember, is something that is like this, and it's like this. Okay, but as time progresses, the wave moves along to the right, so maybe it looks something like this, right? And it could go on further as time progresses, right? But the idea is I want you to see these two because we're going to talk about each of those. So let's talk first about frequency. Okay, so frequency. Do adjacent antinodes have the same frequency? So we're talking about this guy right here and this guy right, sorry, this is one antinode. Here's the next one. Do those have the same frequency? Well, the answer is yes. In fact, all the particles along the wave are going to have the same frequency. right? Because this particle here is going to take the same amount of time to go down and back as this guy up here to go down and back, right? Because it's a standing wave. This whole thing is traveling together. It goes down together, and then it comes back up together. So every single thing on that piece of the wave, inside, between one node and the next node, those are all moving with the same frequency, right? To go from the top down to the bottom, back to the top, to complete a full cycle. Okay, now that's the same case in a traveling wave, right? Every single particle is going to have exactly the same frequency, right? From one point until it repeats, till it goes through a whole wave. That's true. Okay, so do adjacent antinode nodes have the same frequency? Well, yes. It's going to take this antinode the same amount of time as it's going to take that antinode. Okay, so that's pretty straightforward there. All right. Next question is, take away that, do they have the same amplitude? Well, antinodes do, right? And I'm going to address another question while we're looking at this, but the amplitude of that antinode and the amplitude of this antinode are the same. All right? But do all particles within that arc have the same amplitude? And the answer to that question is no, because this particle right here only has an amplitude of that much in a standing wave, right? This particle over here only goes up and down that much. And so within one antinode, within one area, from one node to the next node, within one arc, each of those particles is going to have a different amplitude from the others. Okay? Now that's very unlike my traveling wave over here. Right? The traveling wave, every single particle, as the wave moves over to the right, every single particle goes to the top, and then it goes down to the bottom of the wave, and then it goes back up again. And it continues that, and every single particle in the wave does that exact same thing because the whole wave passes through all of the medium. Okay, so that's another way in which standing waves and traveling waves are different. Okay, is that in a standing wave, the amplitude of each of the particles is different, whereas in a traveling wave, all the particles have the same amplitude. Okay, now recognizing that, we do recognize that the answer to the original question is yes. The adjacent antinodes will have the same amplitude, but particles within that wave will not. Okay. All right, last one. Do they have the same phase? Okay. Well, that means, remember, phase means that they're doing the same thing at the same time. And that is a definite no for adjacent antinodes. This guy right here and this guy right here, they're doing exactly the opposite thing. When this one is up, this one is down. And when this one moves up to the top, then that one's going to be down. Right? So they're actually pi out of phase with each other. There's a phase difference of pi. Okay, and that's one of those things that we talked about, and hopefully we'll talk about in a later video here in a second. Okay, so recognizing that they do have a phase difference. Okay, in a traveling wave, those are completely different, right? Different particles along the wave can be in completely different phases, right? And we've talked about that before. The one thing to recognize here is that all the particles that are on this part of the wave, that are in this arc between that node and this one, those are all in phase with each other. Because when this one is moving down, that one's moving down, and they're all moving down at the same time. They're all going to be here in the middle at equilibrium at the same time. They're all going to get down to their minimum at the same time, right? So they're all doing, even though they have different amplitudes, they all get to their maximum minimum amplitudes at the same time, and so therefore they are all actually in phase with each other. However, this arc and that arc have a phase difference of pi. All right? Okay, moving along. Last one here. Hopefully. Okay. Cello string vibrates with a fundamental frequency and wavelength lambda. What are the frequency and wavelength of the fourth harmonic? Okay, so this is a standing wave on a string, which is going to be a little bit different. Okay, so fourth harmonic, well, what does the first one look like? Okay, well, the first one looks like this, right? That's the simplest way that I can have a string vibrating. is that it goes this way and then it comes back down the other way, and that's my first harmonic. Okay, so that means that I have a frequency of F and a wavelength of this. Okay, now recognize that that wavelength is a whole wavelength. Sorry, would be like this. That would require 2 lengths of the string. One string is half of a wavelength. Okay, or you could say that 2 lengths of the string are 1 wavelength, right? I'm going from one node to the next. A full wave needs to have needs to have 2 antinodes there, right? This is just 1. Okay, so that's one thing to recognize. Now when I get to the 4th harmonic, what is that going to look like? Okay, well, same string. Okay, I'm going to try to keep it more or less the same length, same string. The 4th harmonic means that I need 4 of these arcs. Okay, so I'm going to need 1, 2, 3, 4. Okay, and just kind of pretend that those are all the same. All right, so I've got 4 there. Now how long is a wavelength? Okay, well, a wavelength now is only half of the length of the string, right? There's 1 wavelength right there. Okay, the big idea, of course, here is that we know that V equals frequency times wavelength. Well, what's happened to the wavelength here? Well, the wavelength went from this down to this. The wavelength is a quarter of what it used to be, right? It used to be half a wave for this whole string. Now I've got 2 waves there, which means it's a quarter. This arc takes a quarter as much space as it used to. It used to take the whole string, and now that arc only takes a quarter of a string. So if the wavelength is 1/4 of it used to be, in order for the speed of the string to stay the same, which it should, because the string's not changing itself, that means the frequency must be 4 times as big as it used to be. So therefore, the frequency is 4F, 4 times the original frequency, and the wavelength is a quarter of what it was before. Okay, and so those ideas kind of help us understand what's going on here in the big picture. All right, hopefully that's helpful. Later.